AC interference, corrosion and the AC mitigation industry. Is the science being made more complicated and more expensive than it needs to be? A question raised by Luis Repenado from Colombia. Luis Repenado recently raised an interesting question about the expensive computer-based modelling and simulation software used in the corrosion engineering market to analyse electrical interference and design AC mitigation systems. Louis wrote, "Good evening, Roger. Hope things are well in the UK. I'm trying to gain a clearer understanding of how the expensive computer-based modelling and simulation software sold in the corrosion engineering market, used for analysing electrical interference processes and delivers results, as well as how it designs AC mitigation systems. I fully understand that coatings such as FBE possess high dielectric strength, which is verified during construction using holiday detectors rated up to 20 kilovolts. I also understand that AC leakage currents and short circuit currents resulting from single-phase faults always travel through the soil, grounding systems and shield wires back to the generation sources to complete the circuit." Louis has identified an important subject, and I want to use his comments as a starting point for a wider discussion. My response to Louis was, there is a fundamental question that I believe needs to be asked. What exactly is happening to the pipeline when alternating electrical fields and currents are present in the ground? Let us start with something very simple. Alternating current alternates. It goes backwards and forwards. In the UK, normal electrical supply alternates at 50 cycles per second. In other countries, such as the United States, it is normally 60 cycles per second. The electrical charge moves in one direction and then reverses. That is fundamentally different from direct current, which flows in one direction. A battery, for example, produces a DC potential. It does not spontaneously produce alternating current. It produces DC current, direct current. To obtain alternating current, AC, from a battery or other DC source, an electronic circuit such as an inverter or oscillator has to convert the DC into an alternating waveform. That distinction is important when we start talking about corrosion. Corrosion is an electrochemical process. At a corrosion site, metal is oxidized. In simple terms, electrical charge is transferred away from the metal as the metal atoms participate in an electrochemical reaction. That is fundamentally different from simply asking, there is an AC in the soil, therefore AC is corroding the pipeline. That statement is far too simplistic. The real question is, does the alternating electrical disturbance produce a net transfer of charge from the pipeline that results in metal loss? That is where the science becomes interesting. Look at what happens to a coated pipeline. When a pipeline is manufactured and constructed, it is normally protected with a coating such as FBE or another pipeline coating system. Before the pipeline is buried, the coating is inspecting for defects. One of the familiar instruments for the purpose is the holiday detector. The term holiday has nothing to do with taking a holiday. It refers to a defect or discontinuity in the protective coating. The detector applies a high voltage between the pipeline and the surrounding environment. If the coating is intact, the high dielectric resistance prevents the circuit from being completed. But if there is a coating defect, the electric field can find a path through the defect to the metal pipe. The instrument detects the resulting electrical discharge. It rings. This is a very useful demonstration because it shows something fundamental. The coating separates the pipeline from the surrounding electrical environment, except where a coating defect provides a conductive path. Now put the high voltage transmission line above the pipeline. Imagine a high voltage transmission line crossing or running close to a buried pipeline. The transmission line creates alternating electrical energy. This creates electrical fields and can induce voltages and currents into nearby conductive systems. And, as Luis correctly points out, fault currents and leakage currents can involve the soil, grounding systems and other conductive paths as the electrical circuit seeks to return to its source. So we have to distinguish between the electrical disturbance in the ground and the electrical reaction occurring at the pipeline. These are not necessarily the same thing. What happens at a coating fault? Now we arrive at the important part. Suppose the pipeline coating is intact except for a very small defect. The surrounding ground is subjected to an alternating electrical influence. At the coating fault, the pipeline becomes electrically coupled to the surrounding electrolyte. The alternating electrical field can therefore drive current through the defect. But here is the question that I believe deserves much more attention. Does the positive half cycle simply reverse the process produced during the negative half cycle? If it did, we would need to ask whether there is any net charge transfer associated with metal dissolution over a complete cycle. That is why simply detecting AC current is not by itself proof of AC corrosion. But there is a complication. the interface is not an ideal resistor. The metal electrolyte interface is an electrochemical system. It is not simply like a piece of copper wire. The interface contains electrochemical reactions, polarization effects, capacitance, and other non-linear behavior. Once you have a non-linear interface, the situation becomes more interesting. An alternating input does not necessarily produce a perfectly symmetrical electrochemical response. This is where rectification and other forms of current asymmetry can become important. In other words, the AC waveform may alternate, but the electrochemical response does not necessarily have to be perfectly symmetrical. That is the scientific question that needs to be investigated rather than simply assuming that AC causes corrosion. And that brings us back to the pipeline. A pipeline with a coating defect can act as part of an electrical circuit. The surrounding ground can be subject to alternating electrical potentials. The pipeline can therefore experience alternating current at coating defects. But what matters from a corrosion point of view is the net anodic current and the resulting metal dissolution. That is why I believe we need to stop confusing AC current in the ground with corrosion current leaving the pipeline. They are not automatically the same thing. What about natural corrosion? Now consider a pipeline that already has a natural corrosion cell. The pipeline itself can contain anodic and cathodic areas. At the anodic area, metal is lost. At the cathodic area, a corresponding reduction reaction takes place. The coating system is therefore already an electrochemical circuit. Now, introduce an external alternating electrical influence. The important question becomes, how does that electrical energy interact with the existing corrosion cell? Does it merely cause an alternating perturbation? Does it produce a net current shift? Does the interface rectify the waveform? Does it change the local polarization? Or does it actually increase the long-term metal loss rate? These are questions that should be answered experimentally. This is where I become concerned about AC mitigation industry. We now have a very large and sophisticated industry built around AC interference modelling, computer simulation and AC mitigation. There are expensive software packages, there are complex mathematical models, there are grounding systems, there are mitigation wires, there are gradient control systems, there are decoupling devices, and there are many other engineering solutions. Some of these technologies may have legitimate applications, but the existence of expensive technology does not automatically prove that the underlying explanation has been correctly understood. Complexity is not proof of scientific correctness. And expensive equipment is not proof that the problem cannot be solved more simply. My experience has led me to a different question. During my career in corrosion control and cathodic protection, I have repeatedly seen situations where the important thing was not to make the problem more complicated, but to identify where the corrosion current is actually leaving the pipeline metal. If we can identify the location where the current is leaving the pipeline, then we can ask a much simpler question. Can we provide another path for that current to go into the electrolyte? This is where the sacrificial anode principle becomes interesting. Instead of allowing the pipeline metal to act as the anodic source of the current, a sacrificial anode can be deliberately connected to the system. The anode becomes the metal that is consumed. The pipeline is protected. This is not a new principle. It is the fundamental principle of sacrificial anode cathodic protection. So why make the solution unnecessarily complicated? If a properly designed sacrificial anode can deal with the current leaving the pipeline at a particular location, then we should ask, why do we necessarily need an enormously complicated and expensive AC mitigation system? The answer should not be decided by marketing, it should be decided by measurement. Put the systems to the test. Measure the pipe to soil potential, measure the current direction, measure the corrosion rate, measure the metal loss, then compare the results. That is science. This is also where cathodic protection network blockchain comes in. This is exactly the sort of question that the cathodic protection network blockchain is intended to encourage. Not believe Roger, not believe the software company, not believe the consultant, but do the experiment, record the measurements, publish the methodology, publish the results, allow other corrosion engineers and scientists to examine them, then repeat the experiment. If the expensive system works better, demonstrate it. If the simple sacrificial anode approach works just as well, demonstrate that too. Let the measurements decide. And what about the Nord Stream discussion? This subject demonstrates while understanding electrical interference is important when examining complex pipeline incidents. When people see a pipeline, electrical systems, soil, coatings and external sources of energy interacting, it is very easy to produce an explanation that sounds technically impressive. But technical language does not automatically make an explanation correct. We need to understand the actual electrical circuit. We need to know where the current originates. We need to know where it goes. We need to know what happens at the metal electrolyte interface. We need measurements. Without it, a computer modelling can become an exercise in producing an answer from assumptions. A computer can calculate a model perfectly, but if the assumptions going into the model are wrong, the answer can still be wrong. That is why experimental verification is essential. The challenge. So, my challenge to the corrosion industry is very simple. Don't tell us that AC mitigation is necessary because the software says so. Show us the measurements. Show us the current leaving the pipeline. Show us the corrosion rate. Show us what happens before mitigation. Show us what happens after mitigation. And show us whether a simple cathodic protection solution can achieve the same result. If it can, then perhaps we have been making the problem unnecessarily complicated. If it cannot, then demonstrate scientifically why it cannot. This is how engineering should work. One final point. I'm not saying that every AC interference problem is imaginary. I'm not saying that every AC mitigation system is useless, and I am not saying that alternating electric fields can never influence corrosion. What I am saying is that we must distinguish between alternating current itself and the net electrochemical corrosion reaction that produces metal loss. The distinction is fundamental, and if the industry is going to spend thousands or potentially millions on analysing and mitigating electrical interference, then the scientific basis for those expenditures should be open to investigation. The question is not how complicated can we make the explanation. The question is whether the explanation is correct. This subject is extensively covered in our online correspondence course. The Cathodic Protection Network is continuing to investigate these fundamental questions in corrosion science, cathodic protection, electrical interference, and the measurement of the corrosion current. Our online correspondence course goes much further into these subjects, including relationships between electrical energy, corrosion cells, cathodic protection, and the measurement of corrosion current. We believe that this knowledge should not simply disappear when the people who developed it are gone. It should be recorded, examined, challenged, and passed on. What do you think? Do you agree with this explanation, or do you disagree? We would genuinely like to hear your comments. If you have experience with AC interference, pipeline corrosion, cathodic protection, or AC mitigation, tell us what you have observed in the field. If you find this interesting, please like the video and follow Cathodic Protection Network for more discussions about corrosion science and cathodic protection. The object is not to win an argument. The object is to find out what is actually happening. Thank you for listening to this. Don't forget to like and subscribe.
And